Hello everyone, and welcome to my presentation for the M5 HANA Hackathon, building on the M4 binary classification with putting on a couple of new components. And my project will be focusing on developing an AI-driven stroke prediction model that ensures accuracy while maintaining fairness, transparency, and interpretability. And stroke as a leading cause of disability and mortality worldwide, making early decisions quite crucial. However, the AI-driven models in healthcare can introduce bias, potentially leading to unfair treatment recommendations. To counteract these risks, I integrated models and conducted an ethical assessment to ensure accountability and reliability in predictions. Before training the model, I implemented several extensive data processing steps to enhance the reliability and fairness. Now, this involved encoding the categorical variables to work seamlessly with LightGBM, removing extreme outliers using the Tukey method, and that is to prevent the skewed results, and applying various feature scaling techniques, such as the standard scalar, min-max scalar, and robust scalar for numerical variables. A major challenge in the dataset was the underrepresentation of the stroke cases, which could lead to the model disproportionately favoring non-stroke predictions. And to mitigate this issue, I utilized the SMOT to generate additional synthetic examples of stroke cases and boosting the minority group and ensuring the model learns the meaningful distinction between both stroke and non-stroke data points. And for training, I selected LightGBM, a high-performance gradient boosting algorithm designed for structured data. However, the machine learning models can exhibit bias that may disproportionately affect the certain demographic groups. To address this, I applied the fairness exponentiated gradient boosting to enforce demographic priority constraints, ensuring the predictions remain equitable across the different groups. And to evaluate the model reliability, I employed the stratified k-fold cross-validation, which maintains consistency across the different training examples. And the model demonstrated a strong performance, achieving an accuracy of 95.24% plus minus 0.35%, a precision around 94.35%, a recall of 92.39%, and an iPhone score of 0.93. In medical applications, recall is particularly crucial, as failing to identify stroke cases could have severe consequences, where a model effectively balance the precision and recall, optimizing for fairness, introduced the trade-offs that require carefully monitoring to assess this fairness. I calculated the key fairness matrix, including a demographic priority difference of 0.0162 and an equalized odds difference of 0.0173, both of which indicate that the model does not significantly favor any particular demographic groups, and although slight disparities remain. And to ensure the model transparency was a priority, systemic is critical in healthcare applications. And to understand how predictions were made, I employed multiple explainability techniques. First, I conducted feature importance analysis using implementation and feature importance, which revealed that age had the most substantial impact on predictions at 40.7%, followed by a glucose level and BMI. And surprisingly, the hypertension and heart disease have a lower than expected influence. And to validate these findings, I applied the SHAP values, which reaffirmed that the age was the most significant predictor, while also highlighting the higher glucose levels and BMI increased the stroke risk. Notably, the gender had minimal impact, suggesting that the model did not exhibit gender-based bias. and to interpret the individual predictions, I utilized the LIME, which provided insights into the factors that are contributing to specific model outputs and ensuring alignment with medical knowledge. Additionally, since LightGBM is a complex model, I built a decision tree surrogate model to approximate its logic in a more interpretable manner. And the decision tree analysis confirmed the age was the dominant factor in stroke prediction, with additional influence from work type and BMI, while gender and residential location had minimal impact, reinforcing the fairness. And beyond the performance matrix, ethical consideration played a crucial role in this project, analyzing the dataset that revealed that urban populations exhibit a higher prevalence of stroke, likely influenced by lifestyle and disparities in health care access. One of the primary ethical concerns was the strong influence of age on predictions. While age is established medical risk factor, it is essential to ensure that it does not advertently lead to unfair healthcare prioritization. To further mitigate bias, I explored the potential improvements, including adversarial de-biasing, a technique that leverages the secondary model to counterattack bias the decision patterns, and reweighting methods, which adjust the significance of underrepresented groups during training, where fairness constraints help to reduce disparities. Ongoing monitoring is necessary to ensure that the bias did not merge in real-world deployment. Overall, this project successfully integrates responsible AI principles to the stroke prediction model that balances the accuracy, fairness, and interpretability. From a real-world perspective, this model can have significant applications in healthcare. It can assist hospitals in detecting stroke risk earlier, allowing the medical professionals to prioritize the high-risk patients, support the public health research by identifying high-risk populations, and enhance the AI-assisted diagnosis to reduce the workload on healthcare professionals. However, as an AI adoption in healthcare growth, continuous fairness monitoring remains critical to prevent unintended bias from emerging over time. Looking ahead, the future improvements could include integrating cultural inference techniques to uncover deeper relationships in stroke risk factors, and expanding the data sets to ensure broader representation across diverse populations, and conducting a real-world clinical trials to validate the model's effectiveness in medical settings. That's so much for today. Thanks for your close attention.